Landing Distance Assessment, Understanding the Regulations and Preventing Overruns. This module discusses landing distance assessments for a transport category turbine-powered airplane and how they relate to the landing distance available, or LDA. As pilots progress from smaller equipment to larger, more complex airplanes, landing distance determination becomes a much more important facet of airplane performance. Unfortunately, landing overruns continue to occur. One important aspect of minimizing these events is for flight crews to gain a more complete understanding of landing performance. This module will review two different and unique landing distance calculations. For identification purposes, we will refer to these as pre-departure planning and time of arrival landing assessment. The landing distance for a transport category airplane is defined by the certification rules in Part 25. This certificated landing distance starts at the point where the airplane main wheels are 50 feet above the runway surface. It continues through a nominal air distance and includes time delays, allowing for the transition into the stopping configuration. The landing distance ends at the point where the airplane comes to a complete stop. The use of deceleration devices, such as normal wheel brakes with anti-skid action, spoilers, and lift dumping systems, may be used in determining the landing distance. However, the use of thrust reversers is not considered when calculating the certificated landing distance. Landing distances based on these certification rules reflect the maximum capability of the airplane and are generally shorter than the landing distances achieved in normal operations. Prior to 2002, the certificated landing distance was based on a stabilized approach and an approach speed not less than 30% above the stalling speed in the landing configuration, or 1.3 VSO. A speed greater than 1.3 VSO could be used if needed for acceptable airplane handling characteristics. Over the years, this final approach speed became known by the term VREF, or Landing Reference Speed. However, this particular V speed was never part of the certification rules. Beginning in 2002, the term VREF was officially incorporated into the Code of Federal Regulations as a defined V speed. Since this change occurred at the same time the rules governing stall speed calculation were amended, VREF differs slightly from its previous use. VREF as now defined may not be less than the reference stall speed, or VSR, which is the speed at which the stall speed in 1G flight corresponds to the point of maximum lift coefficient just before the lift starts decreasing as angle of attack is further increased. VREF must also be above the landing minimum control speed and any speed necessary to demonstrate acceptable airplane handling characteristics. With the adding of VREF to the regulations, the rule defining approach categories was also amended. For airplanes where VREF is defined by the certification rules, the approach category for that airplane is based on its VREF speed determined at its maximum certificated landing weight. The landing distances determined during certification are established with full awareness that operating rules require additional factors to be added when determining the minimum operational field lengths for landing during normal line operations. The operating rules for Part 121, Part 135, and Part 91K require that the landing distance demonstrated during certification remain within a specified percentage of the runway length available for landing at both the destination and alternate airport. As a result, these rules establish a minimum operational field length for landing. This requirement does not apply to Part 91 operators, but voluntary adherence to these rules is encouraged. These operating rules impose a limitation on takeoff weight, such that you do not plan to arrive at your destination or alternate airport at a weight that will not allow you to meet the landing distance requirement specified in the operating rules. Therefore, any planning intended to demonstrate compliance with these rules must occur prior to takeoff, or as condition of dispatch, for those operators subject to dispatch requirements. When required by the operating rules, the landing distance demonstrated during certification must permit the airplane to come to a full stop within 60% of the landing distance available. Another way of saying this is that the landing distance demonstrated for certification must be multiplied by a factor of 1.667, or divided by 60%, to define the factored landing distance on a dry runway. The resulting factored landing distance is intended to account for operational variables, including piloting techniques, flight path deviations, tire and brake wear, atmospheric conditions, including gusts, and other variables not addressed during landing distance certification. For eligible Part 135 and Part 91K operators, the landing distance demonstrated during certification must permit the airplane to come to a full stop within 80% of the landing distance available. In this case, the demonstrated landing distance for certification is multiplied by 1.25 or divided by 80% to obtain the factored landing distance on a dry runway for these operators. Landing distance data that is published in the Airplane Flight Manual varies widely between airplane manufacturers. Some manufacturers furnish the landing distances determined during certification, in which case pilots are expected to apply the appropriate multiplier 1.667 or 1.25, while others furnish the factored landing distance data for use in complying with the operating rules. Some manufacturers provide both the certified and factored landing distances, as in this example. A few manufacturers do not provide landing distance data at all, but rather provide data on the maximum allowable landing weight as a function of landing distance available. Let's use the data we just looked up to perform our pre-departure landing distance evaluation. At 19,200 pounds, the landing distance determined during certification is 2,700 feet, and the factored landing distance is 4,500 feet. Since the landing distance available is 5,000 feet, the runway length is adequate provided the runway is dry. However, if the runway is expected to be wet or slippery at the time of arrival, the operating rules require that the dry runway factored landing distance be increased by an additional 15%. In this example, our factored landing distance increases to 5,175 feet. Therefore, a 5,000-foot runway that is wet is no longer of adequate length for a planned landing weight of 19,200 pounds. It is important to note that this additional 15% increase is not based on demonstrated wet runway stopping performance. Therefore, the wet runway factored landing distance may not provide the additional distance necessary to accommodate actual stopping performance on a wet runway, let alone a runway contaminated by snow or ice. The factored wet landing distance exceeded the landing distance available, so we cannot legally take off. We will need to reduce the planned landing weight. If we multiply 4,300 feet by the wet runway factor of 1.15, the resulting distance is shorter than the landing distance available. Therefore, our takeoff weight must be reduced to a value that permits a landing weight not in excess of 18,000 pounds. Many runways used by transport category airplanes have skid-resistant surfaces, which may include runway grooving, porous friction course overlays, or a combination of both. Runway grooving and PFC surfaces allow water to escape from beneath the aircraft tires traveling at high speed, which reduces the threat of hydroplaning, but does not eliminate it. These surfaces do not drain water from the runway, nor do they increase the friction capacity of the runway surface. A common misconception is that a grooved or PFC runway is considered to be dry for the purposes of applying the 15% increase when the weather reports or forecasts indicate that the runway may be wet or slippery at the time of arrival. Unless otherwise approved by the FAA, if the weather reports or forecasts indicate that the runway will not be dry at the time of landing, then the 15% increase to the factored landing distance must be applied. The intent of this pre-departure planning is to ensure that a flight operation does not begin that cannot reasonably be concluded upon reaching the destination or alternate airport. Pre-departure planning is required by Part 121, Part 135, and Part 91K operators. Part 91 operators are encouraged to do so, but it is not required by the operating rules. At the destination airport, the factored landing distance must be evaluated using the most favorable runway, usually the longest runway in still air conditions, and for the most suitable runway for landing in consideration of wind conditions, instrument approaches available, or other factors that make use of this runway desirable. The evaluation of the most suitable runway is not required when an alternate airport with a runway that meets both of these requirements is designated. These same requirements apply to the alternate airport if one is required. This evaluation is adequate for landing performance planning for routine operations when the runway is dry. The 15% increase required when the runway is wet or slippery is not based on demonstrated stopping performance, but is an arbitrary additive applied to the dry runway factored landing distance. The factored landing distance calculated during pre-departure planning is not a limitation at the actual time of landing. A runway may be used for landing when the factored landing distance exceeds the landing distance available published for that runway. However, an assessment of actual landing distance is recommended. More on that subject in a moment. It is especially important for flight crews to understand that the landing distance data established during certification and published in the AFM is not representative of everyday operational practices and does not reflect operational landing distances. This is true even when the AFM or QRH labels such data as actual landing distance, as shown in our previous example. This is because not all operational factors affecting landing distance are required to be accounted for by certification regulations. The landing distances determined during certification are aimed at achieving the shortest landing distance possible with a test pilot at the controls. To achieve the minimum airborne portion of the landing distance, flight testing and data analysis techniques can result in assumed touchdown rates as high as 480 feet per minute. The approach angle flown during testing may be steeper than the approach angles typically flown on an ILS or visual approach. To minimize the ground portion of the landing distance, the test pilot initiates maximum manual braking as soon as possible after touchdown and continues using maximum braking until the airplane comes to a complete stop. These flight test techniques are not typically practiced by flight crews during normal landings. The certification rules for landing distance data do not require correction factors for runway slope or for non-standard temperatures, and do not normally account for the use of auto brakes, auto land systems, or thrust reversers. However, some manufacturers may provide correction factors for runway slope and non-standard temperature with the knowledge that the AFM landing distance data, as determined during certification, may be used by pilots to assess landing runway requirements during normal line operations. Nevertheless, it is easy to appreciate that the landing distances determined during certification and the certificated landing distance data published in the AFM will be shorter than the actual landing distances achieved in everyday operations. Flight crews may mistakenly assume that the large regulatory margins built into the pre-flight departure landing checks are always adequate to protect against overrun in any potential landing conditions encountered. This perception is dangerously inaccurate. FAA and NTSB data identifies failure to assess actual required landing distance to account for slippery or contaminated runway conditions or any other change condition existing at the time of landing as a significant causal factor in landing overruns. Let's look at a hypothetical landing performance planning example using Chicago's Midway Airport. The pre-departure landing analysis includes a review of current and forecast weather at the destination airport and the alternate airport, and a determination if the landing weight upon arrival will permit the factored landing distance to be less than or equal to the landing distance available. The operator must evaluate the longest runway in still air conditions. They must also evaluate the most suitable runway given the weather conditions and approaches to be used unless an alternate airport is designated. Using Chicago Midway as our destination airport, for our estimated time of arrival, Runway 13 Center is both the longest and the most suitable runway, given the forecast weather and the ILS approach to this runway. The results of this analysis may be presented to the flight crew in the form of a maximum allowable landing weight on a particular runway. For Runway 13 Center, our maximum allowable landing weight is 19,200 pounds. Another option available is to use the data and procedures provided in the airplane flight manual to determine the dry or wet runway factored landing distance required at the airplane's estimated landing weight. The dry or wet runway factored landing distance, as applicable, must not exceed the runway's landing distance available. This pre-departure planning does not ensure that the airplane can safely land on the runway in use at the time of arrival.
Chicago Midway Information Romeo 2251 Zulu. Wind 150 at 7. Visibility 3 miles. Rain. Ceiling 600 broken. 1,500 overcast. Temperature 2. Dew point 0. Altimeter 29er 89er. Approach in use ILS runway 31 center. Landing and departing runway 31 center.
FAA SAFO 06012 recommends that all turbojet operators have procedures to ensure that a full stop landing with at least a 15% safety margin beyond the actual landing distance can be made on the runway to be used, in the conditions existing at the time of arrival, and with the deceleration means and airplane configuration that will be used. While this assessment does not mean that a specific calculation must be made before every landing when conditions deteriorate, or the landing runway changes from the planned runway used in pre-flight planning, a calculation or other method of determining the actual landing distance capability should be accomplished. This assessment can take many forms. One example would be determining before the flight that you can land with at least a 15% safety margin on the planned arrival runway at maximum landing weight in the planned landing configuration with 10 knots of tailwind in any runway braking condition better than poor. Your assessment at the time of landing may be as simple as verifying that the landing would be conducted within those parameters. This landing distance assessment should be accomplished as close to the time of arrival as practical, taking into account workload considerations during critical phases of flight and using the most up-to-date information available at the time. Pilots should also look beyond the current conditions and plan for the worst-case conditions. Additionally, operators should use the most adverse reliable braking action report if available, or the most adverse expected conditions for the runway, or portion of the runway that will be used for landing when determining the landing performance assessment. When conditions are such that the runway surface conditions vary along the runway, such as braking action fair first 2/3 but poor the last 1/3, then the most conservative or worst condition for the portion of runway to be used should be used for the landing distance assessment. Based on the ATIS information received, what would you consider when performing a landing distance assessment? At a minimum, we should consider the operational impacts of the wet runway and the tailwind. The assessment may be based on manufacturer-furnished advisory landing distance data for use on wet and contaminated runways. This data is an analytical computation that adjusts landing distances determined during certification for the detrimental effects on braking performance resulting from a particular type of contamination. While the data is not based on actual flight testing, it does allow flight crews to assess actual landing performance based on the anticipated landing conditions. Once the actual landing distance is known, SAFO 06012 recommends that a 15% safety margin be added and that the resulting distance be less than the declared landing distance available, unless imminent risk to continued flight makes this landing imperative. For those airplanes where advisory contaminated runway landing distance data is not available, SAFO 06012 provides factors based on the reported runway condition or braking action reports to determine the minimum runway required for landing. These factors are applied to the factor dry runway landing distance used in pre-departure planning and include the recommended 15% safety margin. After this initial landing distance assessment is complete, pilots should monitor for deteriorating runway conditions prior to landing and base their decision to continue on the most conservative assessment of the aircraft's stopping performance on the runway. In some cases, contradictory information concerning runway conditions or braking action reports may force the flight crews to apply their best judgment about which information is likely to be most accurate. The receipt of new or updated information on runway conditions may result in the reevaluation of a previous decision to land. In a case where uncertainty of landing distance remains, it may be appropriate for the pilot monitoring to quickly reference the QRH or TAPP data, or in other cases, the prudent use of a go-around and a holding pattern at a safe altitude to reevaluate the decision to land or divert may be the best decision.
Citation 938 Sierra Charlie, cleared to land, runway 31 center. Wind 140 at 8. Reported braking action fair touchdown, poor rollout.
Based on the previous time of arrival landing assessment, but now with a report of deteriorating runway conditions, what would you do? Operators of turbojet airplanes are encouraged to develop standard operating procedures for flight crews to assess landing performance based on the runway conditions actually existing at time of arrival. Ultimately, it is up to the crew, based upon the amount of time, type of tools, and information available to them, to decide the most appropriate time to accomplish this assessment and how detailed it must be based on the situation facing them. For more information on this important topic, flight crews are encouraged to review Safety Alert for Operators 06012, Landing Performance Assessment at Time of Arrival, and Advisory Circular 9179, Runway Overrun Prevention.